we will move into something more organic after some of these inventions. And I thought that I will start with asymmetric synthesis, also because the last year's Nobel Prize was again given in this area. Okay, and it's really something which is becoming increasingly more important. All of you have seen this before, or many of you have, and today asymmetric synthesis it continues to be an important area. Obviously, you can imagine that the 2021 Nobel Prize has gone to that area again, and that's because we know that there are drugs which are very good in curing some diseases, but the other enantiomer, okay, can in many cases be very dangerous. Okay? So ever since that knowledge became available to people, they started to focus on how do we make drugs with just the right required enantiomer, and not to just leave the other enantiomer there. Okay, so there has been a huge change that has taken place, especially in pharmaceutical research, based on this solid piece of evidence that well, there are some cases where the opposite enantiomer is not necessarily harmful, but there are many cases where it is distinctly harmful. And so that has given a huge boost to this area. Now, one of the things which I also thought is interesting to mention is that some of the topics that we cover, of course, I'm looking at it really to convey excitement in innovations, but it's actually helped some of the previous students in identifying the topics for their PhD. I got this from one of the students from one of the previous batches, and he says that he got interested in the area of asymmetric catalysis. It grabbed his attention, and he's working on asymmetric catalysis. And he says, "I'm very thankful to you for the course and helping me to find my interest." So I was quite happy that it actually has served more than one purpose, not only to show you how innovations are actually happening, okay, but also that some of the areas could be of considerable contemporary interest. Okay. I was actually going to give you a introduction based on my earlier lectures, but then I realized that one of the people who got the Nobel Prize has done a great job of actually summarizing some of this history. And so I'm not going to share with you the entire lecture. That I will do later on. But right now, at least the introduction which he gives, which I found quite good. Yeah. Let me go to that.
Very first catalysis Nobel Prize was given in 1909 to Wilhelm Oswald, and Oswald actually was recognized for his pioneering studies on the general physical chemical aspects of catalysis. But Oswald also was very much aware of the fact that enzymes, which were known to be efficient asymmetric catalysts, are by no means different to the chemical catalysts that chemists have made. And there's one interesting vision that Oswald proposed in 1905 in a book review, actually, in which he suggested that one day chemists will be able to create organic catalysts, as he called them, organische Katalysatoren, that rival the selectivity and efficiency of enzymes, but are thermally more stable. And this was expressed in 1905. So quite remarkably, actually, his graduate student, Georg Bredig, in 1910 realized this vision already by describing a cinchona alkaloid catalyzed HCN addition to benzaldehyde, and this is actually a reaction that is also catalyzed by enzymes, and Bredig found in a reproducible way that enantioselectivity was actually obtained in this process. Remarkably though, chemists have at that point chosen to almost completely devote their attention to transition metal-based catalysts. And this is reflected again in a history of amazing Nobel Prize winners. For example, Sabatier in 1912 discovered that finely dispersed transition metal powders can actually catalyze hydrogenation reaction of organic compounds. And along those lines, Haber and Bosch, of course, discovered what is probably one of the most important chemical reactions for our life on this planet, the Haber-Bosch synthesis of ammonia, which is a heterogeneously catalyzed hydrogenation of nitrogen to give ammonia. Bergius developed coal hydrogenation processes, again with the help of heterogeneous catalysts that delivered fuels, and those were at the time, of course, very useful and important. A big change then occurred actually in 1963 when the first Nobel Prize was awarded to work on homogeneous transition metal catalyzed reactions, and that the starting point happens to had occurred in Mülheim, actually, in my institute, the Max Planck Institute for Kohlenforschung, when Karl Ziegler discovered homogeneous transition metal complexes that would catalyze polymerization reactions of ethylene and propylene that he and Nutter studied and won the Nobel Prize for in 1963. And that marked the beginning of homogeneous transition metal catalysis. The next 3 Nobel Prizes in this series also went to that area. The one that is probably the most relevant for my presentation today and for this Nobel Prize is the Nobel Prize to Knowles, Sharpless, and Noyori, given in 2001 for their pioneering contributions to asymmetric catalysis of redox reactions, hydrogenations, and oxidation reactions. And only 4 years later, another Nobel Prize was given to a homogeneous transition metal catalyzed reaction, the olefin metathesis, to Schrock-Grubbs and Chauvin. And only again 5 years later, another Nobel Prize for the same general area was given to Heck, Negishi, and Suzuki for their pioneering studies on cross-coupling methodologies using transition metal catalysts. So you can say basically the last century was the century of transition metal catalysis. The only exception was actually the recent Nobel Prize to Frances Arnold for her pioneering contributions to the directed evolution of enzymes, biological catalysts that then can be more efficient or catalyze reactions that are unknown in nature. And so with this background, you probably understand the situation that I found when I was a graduate student in the mid-90s, and that was chemists were essentially convinced that when it comes to asymmetric catalysis, the selective production of mirror image molecules, there are only 2 options available. You can either use enzymes, and as I said, this was already known to Ostwald at the time in 1905 or even before that, or you can use synthetic soluble transition metals as reflected with a Nobel Prize in 2001 to Sharpless, Noyori, and Knowles.
I'll again pick up his lecture so that, we understand what is today the state of art. I will send you the Nobel lectures of some of these people that Benjamin List talked about, starting from Ostwald. And I was just fascinated to read Ostwald's Nobel lecture. While Ostwald has contributed in many areas, Ostwald says that he was extremely happy that his work around catalysis is the one that was recognized by the Nobel Committee. Ostwald is the one who, for the first time, unraveled the acid and base catalysis of esters, and that's how this whole business of relating rates of reactions with catalysis, that all happened because of the tremendous work done by Ostwald, and for which he got the Nobel Prize. In fact, I would strongly urge you to read Ostwald's Nobel lecture. It's also a bit philosophical. If you can go through the lecture, you'll appreciate the breadth of his contributions. It's just amazing. Ever since the time of Louis Pasteur, and the discovery of chirality, people realized that there are molecules which are being made by nature, which are chiral. And people also realized that there are many synthetic molecules which are of interest, which also would be chiral. And there was an interest from a long time in the whole area of asymmetric synthesis. This is the work that Benjamin List was talking about, which we owe to Ostwald and Bredig. Bredig was an associate of Ostwald. You can see it was published in 1912. And so, what was the significance of this? You see, I mean, till that time, all the work that was done by people like Louis Pasteur was all on enzymes, and they could catalyze asymmetric synthesis with enzymes. Okay? But this was the first time when a natural compound, of course, but not an enzyme. So these are alkaloids, these Cinchona alkaloids. That's what he mentioned about. And so things like, quinine, okay, these are the kinds of molecules these alkaloids are, okay. And it was this simple isolated single molecule, okay, which was used by Bredig, okay, in carrying out the hydrocyanation of an aldehyde, benzaldehyde. Okay. And so obviously there's a prochiral center, and when you add HCN, this carbon becomes chiral, okay. And what Bredig had shown is that you get an optically active compound, and so this was the first time, that a non-enzymatic compound, but still derived from nature, was used. So that's really the significance of Bredig and Ostwald's work, in this area. And Ostwald does mention that he thinks that there is really no significant difference between nature's catalysis and the things that we do in the laboratory. And he basically was urging people to draw inspiration from nature's catalysis to do such things in the laboratory. Benjamin List mentioned about the Nobel Prize, which is closest to his work, which is the one by Knowles and Sharpless and Noyori. Okay, and he talks about how they made a significant stride in asymmetric hydrogenation reactions as well as in asymmetric oxidation reactions. There cannot be too many things more fundamental than that, hydrogenation and oxidation reactions. Okay, but before coming to that area, I thought I'll also tell you a little bit about how the interest in hydrogenation, catalysis of hydrogenation, actually began. And just as Benjamin List has said, it's surprising that although Ostwald had pointed out that, and they have got evidence that there are certain organic catalysts which can do asymmetric synthesis. But as he said, for whatever reason, all of the efforts got directed towards metal catalysts. And so it's very interesting to understand why did that happen. Okay? And it happened really because of a very, very important work which was done by Henry Moissan. You have even one of you has covered Henry Moissan in your presentation, okay? And Moissan, after he made acetylene from calcium carbide, when he basically was able to use his electric furnace to make calcium carbide, and then that he was able to get acetylene, Moissan was interested in studying the interaction of unsaturated molecules with metals. He had that as an interest, and so what he did was that he contacted acetylene okay, with metals like nickel, cobalt, and iron, and even platinum black, and he wanted to see if he can make some products out of this. Okay. But what he was very disappointed by was that when he exposed the acetylene to these metals, he found that there was a lot of black carbonaceous material, okay, and which he thought was carbon, rightly so, and there was a gas which was being evolved. And so Moissan assumed that that gas is hydrogen, okay, and there was also some liquid product which he got, and he kind of assumed that it is benzene. I mean, that's the assumption. And Moissan got completely disinterested in pursuing this work further. He said, look, I mean, I wanted to see if acetylene is interacting with metal, and look at all this rubbish that I have ended up forming, So he just, as far as he was concerned, he put a full stop to this line of research. But let me also tell you that Moissan was interested because around that time there was also a lot of work in the interaction of nitrogen peroxide with metals, which were forming things like weak interaction. And that is probably what actually got Moissan interested in the first place. Now, there's always somebody who likes to capitalize on certain observations, and especially an observation made by a man of the fame of Moissan. I mean, you don't just rule out that kind of an observation. Forget about whether Moissan himself was interested or not. So this person, Paul Sabatier, and both Moissan and Sabatier both were French. So I'm sure that would have been another reason for his wanting to work on something which Moissan had done. And so he asked, Sabatier asked Moissan that you have reported this, and I just wanted to check with you whether if it is all right if I carry out some further studies on your observations, And Moissan said, yeah, you go ahead, you do it, because he was not interested. He was not interested in all of this, okay. And but such was Moissan's fame that nobody would dare to even repeat his experiments or copy his experiments without actually taking approval from Moissan. So that's what he did. But then I think that he probably still had some kind of a fear, and so he didn't work with acetylene. He just decided to change over to ethylene, and to just carry out the same kind of studies that Moissan did, but substituting acetylene with ethylene. Okay, and then Sabatier, in his Nobel lecture in 1912, is basically describing some of the prior art of Moissan. And the first part I've read out. And then Sabatier says that Moissan explained this curious reaction as being due to physical condensation of the acetylene in the pores of the metal, this condensation producing locally a temperature sufficiently high to break down part of the acetylene into hydrogen and carbon. That's what Moissan thought. Okay, and to transform the rest into benzene and other hydrocarbons, as in the famous experiment of Berthelot. Okay, a more thorough examination would have changed this opinion. The condensed liquids are in reality very different from those yielded by simple polymerization of acetylene at dull red heat. The gas evolved is not hydrogen, but contains large proportions of ethane. So this is what Sabatier found, that whereas Moissan thought it is hydrogen, it's not hydrogen, it's ethane. And then he says, having made certain that Moissan was not thinking of continuing the study of this reaction, I took it up myself And first of all, together with Senderens, I made a similar test on ethylene. When a stream of ethylene is directed onto nickel, carbon, or iron, which has been freshly reduced and kept in the region of 300 degrees centigrade, intense incandescence of the metal with deposition of large quantities of carbon due to breakdown of the ethylene occurs. So he was able to get something very, very similar to what Moissan had observed. But he says, however, the gas which leaves the apparatus is not hydrogen, but consists mainly of ethane. Okay? Now, when he got this, what could be another line of experiment which perhaps he could have looked at? You understood what he's trying to say, that he exposed the ethylene to this metal and he got ethane as the product in the gas phase. Okay. Now, is there any other way to carry out this experiment? Some variant of this experiment?
Sir, I had one doubt.
Yeah.
Sir, so what happened to the liquid? Like he just said that it is different. It is not what Moisan had suggested, but it is something else. But then he does
Yeah,
not say
I
what
think
the
that's interesting. It doesn't say too much about the liquid. Okay, he was focused more on the gas phase. The reason is because you see, I mean, he was starting with an unsaturated molecule and he got ethane. So he said, Moissan is right that it's forming hydrogen. To that extent, he said Moissan is right. But he was perplexed that how is ethane being formed. And his kind of attention got diverted to that. The liquid would have been some kind of oligomerase species out of ethylene. That's a possibility because they also got incandescence, which means they got very high temperatures. And probably what Moissan said, some amount of benzene could have also formed. But his focus was more on the ethane and to understand about the reduction. And so he wanted to see that could it be true that hydrogen is being formed and that somehow is responsible for this. So if you know that, what could be a simple experiment that you might want to try out?
we can like form water by passing oxygen.
No. I mean, to form ethane from ethylene.
So we can rather polymerize ethene to form polyethylene.
No. I'm not saying that. He wanted to know how ethane is being formed. No. See, ethane can be formed in many ways. I mean, it's like if I have a disproportionation of acetylene and part of it goes to carbon and the other part gets reduced, and then I can reduce one part to hydrogen to ethane, right? No. If I can explain both the formation of carbon as well as the formation of ethane, through some kind of a disproportionation process, But the issue was that he took what Moissan said seriously, that thinking that there must be some production of hydrogen, and Moissan thought it was the hydrogen in the gas. So what he did was that he actually did a very simple experiment. He just he took hydrogen and ethylene, okay, and so he says this latter could arise only from hydrogenation of undecomposed ethylene, okay, and no doubt this hydrogenation has been induced by the metal. That part he was clear, that there is a role of the metal and that there has been a hydrogenation of ethylene, otherwise I can't get ethane, okay. And then he did this interesting experiment, and then he says, in fact, if a mixture of ethylene and hydrogen is directed onto a column of reduced nickel, the ethylene is changed into ethane, and the same metal can be used indefinitely to bring about the same transformation. Okay, June 1897. Okay, So this is your first, today what we take for granted, the use of rainy nickel to do hydrogenation of unsaturated compounds. Okay, but it was really this experiment which arose from the work of Moissan, and so what he said is that, look, I want to see that if, for example, hydrogen was being formed, as Moissan is saying, then why don't I take hydrogen separately along with the ethylene and see what happens? He just wanted to see whether there's a change in the behavior or what happens. And now what happened is, because the hydrogen is reducing the ethylene, the decomposition of the ethylene in the presence of the metal is not happening. So it is getting hydrogenated much faster than the decomposition reactions which was being noticed. So that's effectively what was done, and this is what he got the Nobel Prize for. Sabatier, as the person who really invented the hydrogenation of unsaturated molecules with nickel as catalyst. Okay. Now this is also, I thought, and I'll show you plenty of such examples where just like you saw that Mitscherlich really observed the rotation of the plane polarized light, and Pasteur wanted to understand what was happening. Okay, and that is what gave birth to the whole area of chirality. Okay, and likewise, Sabatier, he wanted to understand what were the observations made by Moissan, and in the process, he discovered hydrogen catalysis with nickel. So, I mean, I hope you can see, in other words, there is a lot of also potential in failed experiments, especially if you are reading literature, and you may actually find many observations reported in literature which have not been explained properly. And you may say, hey, why don't I get into this area? I'm good at that kind of work. So let me see if I can do some of this, Okay, is that clear how the birth of rainy nickel catalysis and hydrogenation happened?
Yes.
Okay, this person in Japan, Akabori, he is the one who for the first time, what he did was he took silk fibers and basically deposited metallic palladium. And he realized that, these fibers, which nature gives us, they have a chirality. He was able to do a hydrogenation of compounds like oximes. Okay, and there was a trace amount of chiral induction, not a whole lot. Now is something again very interesting. Okay, and you remember that Benjamin List said that he of course talked about all the work of these great people who worked on heterogeneous catalysts like Haber and Bosch. Okay, but I think people took the work of Moissan quite seriously and started looking at in a more general way on the interaction of small molecules with metals. And I think they went a bit beyond and said, why are we only looking at unsaturated molecules? Let us even look at saturated molecules. Like if I just take a hydrogen molecule, can it interact with a metal? And I think the interest would have arisen. For what reason? Because after all, how is the catalysis happening? How was ethylene getting reduced to ethane? There must be some interaction between hydrogen and these metals. And so this great person, Melvin Calvin, who was working in Berkeley, and for those of you who are familiar with photosynthesis, you know that the dark cycle in photosynthesis is called the Calvin cycle. Okay, and it was Melvin Calvin who unraveled this whole photosynthetic pathway, But Melvin Calvin was really an inorganic chemist. Okay, and so his interest was really in looking at the interaction of metals with other organic molecules, And in the late 30s, Melvin Calvin actually was the first to report that he has been able to find a molecule, okay, where hydrogen is clearly interacting with the molecule, and these were it was a transition metal complex, so it was a single molecule. Okay, it was a metal complex. We are not talking about these metal aggregated structures like solid metal compounds. Okay, alloys and things like that. Okay, it was a specific single molecule, and this was a huge thing. The first time hydrogen had been activated by a isolated single metal complex. So that was very, very important. Okay, and then after this work of Calvin, okay, there was a huge amount of interest in small molecule catalysis. Okay, and the first he talks about Ziegler. It was Ziegler in 1953 is the one who for the first time was able to actually use soluble metal compounds. We are not talking about palladium and platinum oxide and all those kinds of solids, but small metal soluble complexes. And that is what he used in his seminal work on the Ziegler-Natta catalysis, for which he got the Nobel Prize in 1963. So it is not that Ziegler started the work in 1963. He got the Nobel Prize in 63. But the work that he did actually was in 1953. And later on, I will describe to you the Nobel lecture of Ziegler in more detail. Ever since the work of Ziegler, when the use of metal complexes for carrying out catalysis was established, the 60s, the late 50s and 60s, there was phenomenal activity in this area. Okay, and one of the most important was really the carbonylation of methanol, which gave acetic acid, one of the greatest processes invented by the Monsanto company. Okay, and the other was this work by these people, Jack Halpern and others in University of Chicago, where for the first time they were able to hydrogenate a molecule with a metal complex in solution. And later on, this great man, Geoffrey Wilkinson, made what is become very famous as the Wilkinson catalyst. This was a very important compound because for the first time, it was shown that you can carry out hydrogenation reaction in solution at a rate which is comparable to that of heterogeneous catalysts. I mean, that was unheard of, because people knew about nickel and how fast the hydrogenation is, but nobody imagined that you can do hydrogenation in solution, okay, with at a comparable rate. And that's what was possible through this work of Wilkinson, which he carried out in 1965, and he got the Nobel Prize in 1973. What was also done by Wilkinson, and not just by Wilkinson, other people like Jack Halpern, whose name I had mentioned last time, they had unraveled the mechanism of hydrogenation using this metal complex. Okay, and so you can see there are three phosphines. Phosphine is a neutral ligand, and chloride, of course, is a -1. So we are talking about a rhodium 1 complex. The overall complex is neutral, so it must be rhodium +1. Okay, and the mechanism painstakingly that was worked out was that these phosphine ligands they have a certain lability, and they tend to uh, kind of combine with the complex, and they also tend to get out of the complex. So this is one example where let's say a phosphine has left. Okay, and then what happened is that because there is a fair amount of unsaturation around the rhodium, the rhodium can acquire a higher coordination state. Whereas once I've left the phosphorus, there's only three of these there. So what was found is that the kind of activation that Melvin Calvin had talked about, that hydrogen molecule tends to go and attack this metal. Okay, and it does it through what is known as oxidative addition. Okay, so whenever you add across a metal complex, okay, that is known as an oxidation process. That is when I form sigma bonds, like this. Okay, and when it leaves, it is referred to as reductive elimination. Okay, so these are very, very fundamental concepts in single molecule catalysis, oxidative addition and reductive elimination. And these hydrogens, by convention, are treated as hydride, so H minus. Okay, so basically the rhodium now can be viewed as a rhodium plus 3 compound. We started with a rhodium plus 1, and now it become rhodium plus 3, where by convention these hydrogens are considered as minus 1 and the chloride is minus 1. So we have got minus 3 altogether, and so rhodium must be plus 3. Okay, so this was established. Okay, and as I mentioned, these phosphine can come in and out. So what was found is that even after this attack, the phosphine can again come back and complex, so that you have got a 6 coordinate complex. Now, at that point, and rhodium, because it's a fairly large transition metal, rhodium can actually accommodate up to something like, well, normal coordination state would be 6, but if required, it can go beyond that. Okay, so what you can see is that this is just to show this equilibrium of phosphine ligands coming in and going out. Okay, and so after the hydrogen had attacked, if you take a molecule like cyclohexene, okay, the cyclohexene, one phosphine again falls off. Okay, creates the vacant space for the cyclohexene to come and attack, and this kind of a interaction is called as pi interaction, pi complex. So it's not formed a sigma bond; it is the pi cloud which is interacting with the metal. Okay, but then what can happen is that it can switch. Okay, from here to this kind of a situation. Okay, where what happens is now one end of this double bond is attacking the rhodium, and one of these hydrogens is attacking over here, to the other part. Okay, so now I've converted this pi complex into a sigma bond. Okay, over here. Okay, now at this point you have exactly the opposite of the oxidative addition, where you have a reductive elimination. So this bond and this bond are getting knocked off. Okay, and you effectively end up producing cyclohexane. So it will go and attack this. Okay, and what do I get back? I get back my original rhodium compound. Okay, and so the cycle goes on and on. Okay, and that's how cyclohexene, for example, is converted into cyclohexane. Okay, now any questions about the mechanism?
Sir, I
Yeah.
have one question.
Yeah.
In the last step where cyclohexane molecule leaves the rhodium complex,
Yes.
yes, what initiates that step? Because
What initiates the stress? Obviously, what will initiate the stress is really the final driving force, which is that if I make a cyclohexane, it's a stable compound. Okay. So if I were ending up forming a very unstable compound, then it may not happen. But if I'm forming a stable compound, that would obviously drive the process. And all I've done is that I've lowered the activation energy for it.
Yes.
Okay.
Okay.
This is a very good question. That what decides when something will oxidatively add and when something will reductively eliminate, as it happens here. And I presume that ultimately there are two things which are important. One is that the stability of the transient state. Whatever transient you get, is it stable enough? If it is not at all stable, then obviously it's not going to attack. Why would it do that? So there has to be some kind of a stabilization of this. And secondly, when I am eliminating this, I'm eliminating, but I'm also creating the opportunity for another hydrogen to attack. So that's basically the very subtle balance of energies which controls catalysis. Is that clear?
Yes, sir. Yes, sir.
Still, all the focus was only on simple hydrogenation. Okay, there was nothing asymmetric. There was no chiral asymmetric hydrogenation. Now, let me ask you the question. The lecture, from here on, is not about just hydrogenation. We have talked about hydrogenation, but it's only to introduce the subject of asymmetric hydrogenation. Now, if I had this Wilkinson's catalyst before us, and we also knew about the mechanism by which this hydrogenation occurs, now, is there any way you might be able to utilize the complex or the scheme to carry out asymmetric hydrogenation? What can you possibly do? Just don't be so inhibited. Okay. All I'm saying is that, this is all you saw, cyclohexene going to cyclohexane. There's no chirality, there's nothing. But suppose, I wanted to carry out the hydrogenation of something and I want to introduce a chirality. I want to get something in enantiomeric excess. Then, while utilizing this kind of a approach, is there any change that you can introduce which will allow for such study?
Sir, what if that alkene attaches itself in two different positions on that same rhodium, so that
Over
it's
here?
in different directions? Yes. Here it is.
No, no, I'm not asking you to make a chiral compound out of the cyclohexene.
Yes, sir. But if we put it like that, then in the next step, that hydrogenation will be asymmetric.
Where? How? Which one will be asymmetric?
Sir, I was thinking that.
No, because
Probably.
there's no prochiral center here.
No, like not in this one, but where it is.
Correct. Yes, what you're saying is that, in other words, you're saying not with cyclohexene, I'll take some other substrate, okay, which can form an optically active compound after hydrogenation. Is that what you're saying?
Yes.
Correct. That is absolutely right. But the question is that if I have a complex with no chirality at all, can I get a chiral induction to happen? Will it ever happen?
Sir, if we are able to attach the chlorine atom of that rhodium complex, because hydrogen and chlorine both are negative ligands here.
Yeah.
So if we can induce something that chlorine will attack on that double bond.
No, that's okay. But I'm just saying that why should it be chiral induction? See, for chirality, you need to have some kind of a chiral bias. They are all mirror images, no? They're identical compounds. There's no difference in energies. And in the laboratory, if you take any reaction and you'll always get a racemic mixture. Okay, unless you have got some kind of a special catalyst. Right or not?
Yes, sir.
Yeah. So the question that I'm asking you is one, as one of you has very correctly mentioned, I of course have to take some kind of a substrate which will be bestowed with a chiral center after hydrogenation. That's number one. Absolutely. Otherwise, what am I doing? But even if I take that, in the absence of some kind of a chiral bias, a chiral preference, it's not going to do anything. I'll just get a racemic mixture. I'll get both optically active forms. Okay. So I have to introduce some kind of a chiral bias on this system. So I'm asking you, can you think of something through which I can introduce some kind of a chiral bias in this complex?
Sir, there is
Yeah.
in that RH complex, those two hydrogens there, so they are identical, right?
Yeah.
So if we make one of those hydrogen positions very difficult for access,
Right.
then only one hydrogen will be taken up, and then as we see in that cyclohexane example, it
Yeah.
will take up that hydrogen from only one direction.
Okay, from one direction. Yes, but the point is, yes, but it will take it up from one direction, but both directions will exist. I'll get both attack from both directions in equal proportions. There will not be any difference. What else can I do to create a chiral bias? If, for example, I've got a phosphine, okay, and what are these? It's triphenyl phosphine, right? So, for example, you can think about that. Can I attach some kind of a chiral substituent on the phenyl ring? Okay, it will give some kind of a chiral bias, right? Right or wrong?
Yes, sir.
That's the kind of thing I'm talking about. Okay, or you can see that I've got phosphorus. Phosphorus is got let's say 3 substituents. Why should I take all 3 as phenyl? I can take substituents R1, R2, R3, which are different. In which case this would be a pyramidal compound. And I might be able to create an optically active phosphine ligand. Have you understood what I'm trying to say? Is that clear now?
So we change the geometry of the catalyst itself.
Yeah. That's what I'm saying. You have to introduce some kind of a stereo specific, control, okay, which bestows some kind of a chirality. Okay, is that clear?
Yes, sir.
Otherwise, it's a perfectly symmetric compound. It can never induce chirality. Okay. So this is what William Knowles, in the early 60s, he recognized, and he said, look, if I can modify this compound, and so that I can do asymmetric hydrogenation rather than just non-asymmetric hydrogenation, oh, that will be marvelous. It will open up a completely new field. Okay? Now, this is the beginning of William Knowles's lecture, one of the finest lectures. Actually, for that matter, all the lectures are very good, but I would rate William Knowles's lecture as truly very special and a bit easier to understand. You can see that he was working in Monsanto, so not very different from people like Bosch and Langmuir, who were working in a company, okay, and went on to win Nobel Prizes. I'm trying to give a special importance to these kinds of Nobel Prizes because these have had a profound impact on technology. And so when we are talking about innovations in chemical technology, these are the kinds of things that have had the most profound impact. It's not that anything and everything in Nobel Prize necessarily has a some kind of an applied impact. No, it doesn't. Okay? But these ones surely do. I've read a lot of these Nobel lectures, and although most of them talk in a very forthright and humble manner, they're not all equally honest. I feel that some of them are, even at the time of the Nobel Prize, are not exactly telling you the whole story. Okay? Whereas there are others who really have been sort of bearing their chest completely. William Knowles is one of those, and he says actually this account is the story of the genesis of an invention. Mind you how important. It's not actually telling you about necessarily the invention, but how the invention happened, the genesis. And that's exactly what we want. Because I want you all to learn that kind of a story so that you can become that inventor. Okay, that's the whole idea. The inventative process is not clearly understood. Okay? And there again, being very, very truthful that every time is not clearly understood. Okay? But one factor that seems to be important is to have a heavy infusion of naivety. This is very, very important. Are you naive enough to ask stupid questions? What I'm finding is, like, when I'm asking you all questions, I find you all very, very scared to answer. Okay? Because you're not naive. Okay? You think that it will be an embarrassment. Okay, if you were to say something, okay, which is incorrect, and maybe because many of you are very good in your studies and you come first and second and things like that, and that makes you even more inhibited sometimes. That how can I possibly say something wrong? Okay? But I would say learn from people what they're saying. Just don't bother what people are going to say. Okay? You saw how Russell cut off the battery. People would have laughed at him, thought he was stupid, expecting to generate some current without any battery. People would have said, "What are you talking about?" Okay? And I can tell you from my personal experience, when I was, I happened to head one of the CSIR labs for a very long time, 15 years. I was the director from 99 to 2014. And when I went to that lab, and I'll of course describe some of the inventions later on, they in their areas certainly knew much more than I did. I had no knowledge of what they were doing. Okay? But that didn't prevent me from asking what I will call very naive questions. Rather, I will say it facilitated by asking because I didn't know. I genuinely did not know. Okay? And I could therefore ask many, many naive, stupid questions. I'm sure, okay, that 80 to 90% would have laughed behind my back. They may not have been able to laugh straight at my face just because I was the director. But I'm sure they would have had a great laugh behind my back thinking, what an idiot has come to be our director. I'm absolutely certain. Okay? That could have happened. Okay? But I can tell you that in those moments, some of our best inventions were made. Okay? And so please be naive and just shrug off your inhibition. Okay? And in fact, let me tell you, being inventive is not just about how brilliant you are. It's about your emotional disposition. You know, are you capable to have a contrarian view? You know, are you capable of asking something when everybody else is going to the right? Do you have the ability to go to the left and do something? Okay, or is are you just going to gravitate around the leader? You know, so these are basically very important things, and that's why I feel that William Knowles's lecture that he brings this out so nicely. You know, this and people like good enough saying be curious. You know, these are the ingredients of success. There isn't any other magic ingredient. You know, these are the ingredients, okay, of success. So he says, and then very interesting. That is why so frequently it is not the experts that do the inventing, but they are the ones who, that once the lead is established, come in and exploit the area. That's what we are seeing over and over again. You know, the greatest people who said something, they have been relegated to the background. And then he says, with great candor, you know, our work is an excellent illustration of this phenomenon. You know, and you know, so he is not claiming that he is some pandit. I mean, he knows, he's saying that we are actually fairly ordinary folk. But maybe we have been naive and asked some so-called silly questions, and that actually gave us a good opportunity, you know. But does that mean that I am therefore a very brilliant guy? Forget it. Not necessarily. Your brilliance may have been that you asked a naive question. Yeah, to that extent, of course, you're brilliant. You know? But if you therefore associate tremendously high IQ, this, that, forget it. They may not have any of that. Okay, so please don't think that everyone who got the Nobel Prize is a genius. They're not. They are many times ordinary folk, but what they have is qualities which you may not have. Like they might have tremendous tenacity. You may not have that. Okay, they have tremendous patience. So, you know, their virtues will be a different kind of virtue sometimes. Okay. Now, this is again something which he says, and we will see it. I'll emphasize this later on also. And he says, I hate to admit it, but it's much easier to invent in a small, underfunded group. Being lean and hungry is conducive to invention. You know, he's saying exactly the opposite of what I see going on everywhere. You know, we are dazzled by all these fancy machines and this, that, you know, I can do this, I can do that. Okay. And our group has got 35 people doing PhD and another 20 doing postdoc. Okay. And who said, wow, what a great lab. But then there are others who are quietly working away. Okay? Somewhere. Sometimes, you know, just working in a quiet corner actually can be quite conducive. Okay, now let's try and see what actually got William Knowles interested. And as I told you, he was working in Monsanto, a company. And Monsanto, as you know, is one of the greatest companies, chemical companies in the US. Okay, so Monsanto was actually in this type of compounds, like what you call MSG, you know, monosodium glutamate. You know. And frankly, after Chinese food became very popular in the 50s and 60s, okay, and people realized that a lot of this Chinese food taste actually comes from this Ajinomoto, which is the monosodium glutamate. And so there was a huge surge of Chinese restaurants, for example, and this monosodium glutamate became extremely important. Much later, people started banning MSG, saying that it's probably not advisable to add it into food. But in those days, and even now, let me tell you that MSG is put in a lot of dishes. Okay. Now, as you can well imagine, it's got a chiral center over here. This carbon is chiral, right? Okay, four different groups. The hydrogen is not shown. Okay, and so what Noel says is that how were they making these things in Monsanto? In the past, when chiral compounds were needed, chemists have had to use biochemical processes. Okay, which is what Louis Pasteur was doing, for example. Did a lot of work with enzymes. Okay, or make a racemic mixture followed by laborious resolutions. Okay, so like for example, if I just use the Wilkinson catalyst without any chiral bias, and I take some prochiral molecule and I reduce it and I get the compound, I'll end up getting both. I'll make a racemate with the plus and the minus, and then I might have to, in another step, I carry out a chiral resolution. Okay, and so what it says is this kind of chiral separation was quite popular in industries. In fact, I know when we did some amount of the chiral separation of a transition metal compound using a tartrate complex. Oh, I felt such a joy separating out the plus and minus isomers. Okay, because that enabled us to then do some very interesting work. Okay, and what he says is that so resolution was an important thing. Okay, and so in industry the problem is particularly severe since resolution with its numerous recycle loops and fractional crystallizations is an inherently expensive process. Thus, large volume products like monosodium glutamate, L-lysine, and L-menthol have been traditionally made by the biochemical routes. Okay, even though efficient procedures are available to make their racemic forms. So that's why people preferred enzyme catalysis. And they did not like the separation of compound. But let me tell you that things have changed dramatically. Okay, and just to tell you that chiral resolution through fractional crystallization, etc., with some chiral compounds is extremely popular. And today, if you have got some compounds which are very costly, where sometimes even milligram amounts cost you thousands of dollars. Today, you can actually even get chromatographic columns, which are chiral. Okay, so the stationary phase has chirality in it. So I can actually resolve the isomers, by chromatography. And so when there are extremely expensive compounds, actually chromatography is today practiced commercially. Okay? So I'm just telling you that things have changed and will continue to evolve. Then he says, in the early 1960s, we became aware of this problem when we made a paper evaluation of a MSG process. The racemic mixture was easy to obtain, but by the time we had resolved, the projected cost doubled, even though we racemized and recycled back the unwanted D isomer. So they wanted the L isomer, okay, and they were lucky that at least the D isomer could be equilibrated again, and they could continuously reconvert the D into L, through this racemization process. But even so, the cost doubled. Now, imagine if you have a situation where I'm making one isomer which is absolutely useless and I have nothing to do with it. Obviously, then by the time I've separated the pure one out, I mean, the cost can be 3-4 times as high. Okay? So it was not really the best of scenarios. Then it says, it looked as though if one wanted to beat the bug, it would be necessary to have a catalyst which, when an asymmetric center was formed, would direct the reaction to give a predominance of the desired isomer. In other words, what he's saying is, if you take a prochiral molecule and after the reaction it becomes a chiral molecule, then it should be done in a way that the reaction directs it to directly get one optical isomer and rather than getting both optical isomers. Okay? For this purpose, the 100% efficiency of enzymes would not be needed to have something of real value. In other words, what he's saying is that if we could do it synthetically, okay, without an enzyme, then I may not need the enzymes, because enzymes have their own problem. You know, isolating enzymes, etc., is not so easy. Culturing the enzymes, okay, culturing the bugs from which the enzymes are recovered, those are not trivial always. Okay. So then, what you can see is that the most logical way to look at the problem, as I told you, would be that I introduce some kind of a chiral side chain on the phosphine. Okay, so that's what they did. It doesn't require a genius to do that. Any guy with very average intelligence would do that. Okay. Early on, we tried phosphines with a chiral alkyl side chain, and the asymmetric bias was barely detectable. Okay, so they got some asymmetric bias by putting in a chiral side chain on one of the aromatic rings of phosphine. Okay, and it was barely enough. I remember taking a very similar approach. Around 1980. I think 86. At that time, there was a lot of interest in what are known as conducting polymers. There are certain polymers when you like acetylene. If you polymerize, you get polyacetylene, and if you just introduce some iodine vapor, the polymer becomes absolutely like a metal. It's so conducting. Okay, a person called McDermott subsequently won the Nobel Prize for these conducting polymers. And I remember, 86, thinking that, look, I mean, there were also some aromatic compounds like thiophene, pyrrole. So you could make polypyrrole, polythiophene, okay? And those were also very electrically conducting, those polymers. Okay, and I thought exactly the same way that Knowles would have thought that why can't you introduce a chiral side chain? Into that thiophene and pyrrole, and then do the polymerization, and we ended up getting a chiral polymer, okay, which was also conducting. And in fact, I remember we coined the term chiral metal, and it's published. Maybe I'll send you the paper. It's called Towards Chiral Metals. That was the first time that a concept of chirality in a metal was introduced. But it was nothing. It was really just a question of putting a side chain into a straightforward compound like thiophene or pyrrole. Okay. Now, so that's what he did. But then, he really did not get very significant chirality. Okay, chiral induction. And at that time, what Knowles said, and you can see, is that he thought a better approach will be to make the entire phosphine complex itself chiral. That means I have a phosphorus with R1, R2, R3 groups. And because it's got a lone pair, so it's like a pyramidal compound. So there may be if you can make such chiral compounds, that will be nice. That's what he thought. So what Knowles then realized was that yes, I mean what he did was good, but he got a very marginal chiral induction by introducing a chiral side chain. But he felt that if he could make the phosphine ligand chiral, that maybe he'll get a better result, and so that's what he wanted to do. But you see, I mean, there were problems. I think that you all will understand. What would happen if I take a nitrogen with R1, R2, and R3 groups? Will the complex or will the molecule be chiral? You understood, no? If I have a tertiary amine with R1, R2, R3 groups, okay, and the nitrogen lone pair is of course there, would you expect the molecule to be chiral?
Yes.
Yes, you would, isn't it? But in reality, what happens is that you cannot do it, okay, if you have these dangling R1, R2, and R3 groups, because you get what is known as the umbrella effect. In other words, just like, in a strong windy day, you have your umbrella and then it inverts sometimes. So the molecule, these amine molecules, they also tend to invert, and the inversion activation energy is very low, so it will continuously flip flop. So it's very difficult to make an optically active amine, even if you have the R1, R2, and R3 groups, because of this inversion process, which will racemize the whole thing. Okay. Now, these two people, Mislow and Horner, in the 60s, okay, they were doing a similar kind of study, okay, but with phosphorus. So phosphorus comes just below nitrogen in the periodic table, okay, and they wanted to know that do the phosphorus compounds also behave like the nitrogen analogs? I mean, will they also undergo this kind of a flip-flop very fast? And what they were able to show is that the activation energy for this inversion is much higher when you have got phosphorus compounds. Okay, so nitrogen is very, very low, and so it will continuously, you'll get both of these enantiomers. Okay, whereas with phosphorus, this activation energy was much higher. So Mislow was basically interested in very fundamental research. He was not interested in asymmetric synthesis, and he just wanted to really understand the activation barrier and things like that. Okay, and in the process, he had to, of course, make optically active compounds, to carry out this study. Okay, which Mislow was able to do, and Horner was in Purdue, I think. So these are the two people who really made the very early study of the these phosphorus analogs. And what Mislow had found was that, as I told you, the activation barrier is high, and so what Knoll says is mid-60s saw the development of methods for making chiral phosphines by Mislow and also by Horner. Phosphorus, like carbon, is tetrahedral, and when 4 different substituents are attached, can exist in D and L forms. In the case of phosphines, the lone pair of electrons counts as a substituent, and like in nitrogen. Earlier, it was thought that phosphines might pyramidally invert like their nitrogen analogs. But Mislow and also Horner showed they were stable at room temperature. They turned out to have a half-life of a couple of hours, even at 115 degrees centigrade. And so, whereas, if you leave it at room temperature, these compounds remain stable for a long time. So once you have made a chiral phosphine, you can actually carry out reactions with it. So he says, for our contemplated hydrogenations, this stability would be quite adequate. Okay. Then the basic strategy was to replace the triphenyl phosphine of Wilkinson's catalyst with a chiral counterpart. Okay. and hydrogenate a prochiral olefin. That's that's really the direction his research took. So you can see he made these phosphorus compounds. It's got three different R groups: propyl, phenyl, and methyl. Okay, and the lone pair. And he found that these are quite stable. So instead of making a normal triphenyl phosphine, he just made the rhodium complex with this kind of a phosphine compound. And this is the compound that he took for hydrogenation, an acrylic acid derivative with a phenyl substituent. And he looked at the hydrogenation, and he says, from that 1% or thereabout optical activity which he got with a side chain chiral group, when he made the phosphorus chiral, he was able to get a 15% enantiomeric excess, which is not bad. So this is what he ended up getting. Which was quite remarkable. But again, it's interesting, and this is where Knowles' honesty comes in. And he says, we were not alone in having this idea, but were the first to report on it. I think it was discussed in the question session after Wilkinson's lecture on his soluble hydrogenation catalyst at a Welsh Foundation conference. So someone would have asked that, have you ever thought of looking at chiral phosphine and trying to do asymmetric hydrogenation? And probably Wilkinson would have said, yeah, it's a good idea. I'm sure one can look at it, but we have not studied and we are not pursuing that line of research. But that is exactly what was of interest to William Knowles. And this 15% enantiomeric excess greatly boosted his motivation, to pursue this further. That was not the only motivation. There was a bigger motivation. Don't forget that, as I told you, Knowles was working in Monsanto, a company. A company is not going to be interested in your fundamental research and this, that. I mean, that's fine. Okay, they want a product. Okay? And so Knowles would have been under some kind of pressure that where can I apply this stuff, in an important application area. And so he had to justify why he was doing this work in Monsanto. Okay. And then he says something very interesting. While groping in this area, another seemingly unrelated development appeared, which played an important role in our project. This was the discovery that a fairly massive dose of L-DOPA, this is L-DOPA, was useful in treating Parkinson's disease. Parkinson's disease today afflicts a lot of elderly people. Okay? And it was only around that time, around the early 60s, or I think late 50s, that this knowledge first came to light, that the chiral form of the DOPA, this one L form, okay, the L optical isomer, was found to actually reduce the Parkinson's symptom. So there was interest, and the company which was really doing a lot of this work on L-DOPA was this company. It was extremely prestigious to get a job in Hoffmann-La Roche. There was also something very interesting that brought Monsanto and Hoffmann-La Roche together. Monsanto was quite big in the area of vanillin. So vanillin is really this stuff with that aldehyde group, vanillin. Okay, this vanilla flavor again, just like your MSG for Chinese food flavor, was a big thing. Vanilla ice cream, this ice cream. I mean, and it wasn't all natural vanillin. It was synthetic vanillin, which was being used. So Monsanto was very big in the vanillin area. Okay, and I'm not very sure whether it was Hoffmann La Roche or Monsanto, but they realized that if I take vanillin, okay, and if you can react it with this compound, okay, this amino acid, okay, that you can end up making this compound. As you can imagine, you'll get the hydroxyl group. You do a dehydration, you'll get a double bond here, okay, and if you hydrogenate this, you'll get this compound over here, but it'll be racemic. This is the chiral center, okay, and I think what they were doing was that they were making up to this stuff over here, Monsanto, and then they were giving this to Hoffmann La Roche, and Hoffmann La Roche had developed a process for chiral resolution, which Knowles had talked about. That chiral separation was a fractional crystallization by chiral fractional crystallization was a very standard important process. So presumably Hoffmann La Roche had developed the technology by which they got the L form, okay, and then all you do is that you deblock this amine group over here, okay, and you'll end up with NH2, and that is your L-DOPA. So there was a wonderful synergy between Monsanto and Hoffmann La Roche, both taking advantage of their respective strengths, okay, and but this was the problem which really then Knowles identified as a golden opportunity for him, because Knowles said, look, if I can carry out asymmetric hydrogenation on this double bond so that I directly get my L form over here, then there's no need for this chiral resolution. Okay, so, and he said, isn't that what I'm working on? That's what I'm working on. He had already done work, on these acrylic acid derivatives. Like here, this is what is this? This is just an acrylic acid. Over here, it's got a phenyl ring. Okay, here it's got a amino group. Okay, a protected amino group. That's it. And so let's read this. It's quite interesting. While groping in this area, another seemingly unrelated development appeared, which I've read out to you about Parkinson's disease. It created a sizable demand for this rare amino acid because of Monsanto's position in vanillin, which provided the 3,4-hydroxyphenyl moiety. We found that they were custom manufacturing a racemic intermediate which Hoffmann La Roche was resolving and deblocking to L-DOPA. So this is really what he was then after. That's it. He just wanted to make this chiral compound. Okay, and he says this enamide offered a golden opportunity for commercializing this burgeoning technology. Okay, now let me also tell you about L-DOPA a little bit. Okay, we will also encounter L-DOPA later on when we look at the discovery of some very famous hard drugs which were made. After this lecture, I'll tell you about that, once we are through with asymmetric synthesis. So this is tyrosine, L-tyrosine amino acid, okay, and then this enzyme, the tyrosine hydroxylase, this one basically introduces this OH group. So it becomes a catechol derivative. Okay, so you've got an OH over here. Okay? So that's what it is, and this is your L-DOPA. Now L-DOPA as such is not really what actually does the job in Parkinson's disease. It's an intermediate. Okay? And this stuff, once you carry out a decarboxylation, okay, and there is another enzyme, DOPA decarboxylase, okay, so it just eliminates this carboxylic acid group, and you end up getting this. Okay, this is dopamine, okay? And this is the neurotransmitter which was found to really inhibit spread of the Parkinson's disease. This is one of our previous students, Ameya Harmalkar, who had taken this course earlier. And Ameya actually wrote me this email after he had joined Johns Hopkins. And I think that one of his lab mates was actually doing some of the computation of the affinity of binding affinity of L-DOPA, and they were doing a computational work. And it was interesting. And he says, hearing about L-DOPA just took me back to the lectures which we had almost a year ago now, and made me realize how chemistry always matters, even at the biomolecular level. Like last time I showed you another email that sometimes these things you'll be able to connect later on with some work that you might end up doing. So it has a value which goes beyond really teaching you innovation.